Yeah.
Okay. So I hope everyone has received this this notebook, decision trees and KNN, and also this .csv file, drug200.csv. So in case anyone doesn't have access to this, please let us know. And this will just be like a tutorial. So you could run these code cells along with me. And in case of any questions, you can post them in the chat. We have 4 TAs to help us out today. Aparajit, Likita, Pratik, and Niranjana. They have been very helpful in organizing this demo session for you all, and they'll also be assisting you along the way in case of any queries. So yeah, so to just state this problem again for clarity, so we have a data set in this .csv file. So just to show you how it looks like, you can open this in Excel also to just visualize. So we have some patient records. Okay, so we have like so each record is of this form, right? So we have the age of the patient, the sex of the patient, the blood pressure, not like a number, but whether it's like high, low, normal, and for cholesterol level, whether it's high or normal, and the sodium to potassium level. So these are like the features about the patient. And this last column is what we call the target column. Okay, so this is the drug which has been recommended for the patient and it has worked well for them. So we are going to use this data to train our decision tree classifier such that if you're given a new patient record, right, it will tell you, it should be able to tell us which drug to recommend to that patient. And there are 5 drug types in this data set. So drug A, B, C, and XY. So it will tell us which one of these drugs should be recommended to that particular patient. And in the end, we'll also use the another supervised learning algorithm called K nearest neighbors. It's a very simple algorithm, and I'll just brief about it when we get there. We'll also use that algorithm for on the same data set and see how good it's performing. So please let us know if there are any issues, and then I can perhaps wait a minute for you all to set this up. So just if you're using Colab, you can load this data set, or even you can use Jupyter Notebook in your local machine as well. So we can start in a minute. So meantime, so we were discussing about these dependencies in the morning. So NumPys and pandas, as I said earlier, are like extremely useful to deal with arrays and data handling to load your data. And the scikit-learn library has many implementations of different algorithms. So yesterday too, the MLP algorithm also we got it from scikit-learn, and today even the decision tree classifier as well as the K nearest neighbors, right? So even these both algorithm implementations are there in scikit-learn. So we don't really have to program the algorithm or the math behind. This is a very simple way to directly get started with using these algorithms. And sklearn.metrics. So even in the earlier session, we saw for text classification, Mukesh had printed out a classification report which has the precision, recall, accuracy, all that. So we are going to do the same for evaluating our decision tree and KNN, so short for K nearest neighbors. So we'll be using that for evaluating these 2 algorithms. And this set of packages and modules are for visualizing. So, so especially for the decision tree, we want to see how it looks like, with what attributes it has chosen at each level, etc. So it will help us get an understanding of what is going behind the scenes. And that's actually kind of the strongest point about these decision trees. It's very easy to understand why it's giving a certain prediction for a record. So that's why a decision tree is a very popular choice when you for what they call as interpretable algorithms. So yeah, if you're using Colab, you can run this cell and choose this drug200.csv file to load, or you could just run this statement also. So this statement you would have been familiar by now. So we use this read CSV function which is available as part of the pandas modules to load our CSV into a data frame. So let's just do that. Okay, and so before we get started with plugging in our algorithms or anything of that sort, we first have to look at the data itself and understand how many features are there, what are we supposed to predict, and what kind of data types the features are of which kind of data types, etc., and what pre-processing steps we need to take before feeding this data into the algorithm. That's a very crucial step before getting started with any kind of prediction, classification of any of things like that. So df.head, which is this function here, is a useful function to just get a quick glance of the data set. So by default, it prints the first 5 records. So here you can see these are the first 5 rows. So you can see how this data set looks like. So the age, of course, is a number 23, 47, etc. The sex column has 2 labels, right? Female and male. And the BP column has also like high, low, normal, etc. If you see like the sodium to potassium column, that has some floating point values. Okay? Unlike this age column, which is just like an integer, this has like a floating point number, decimal number. And then the drug column, which is our target variable. So we can see there's a mix of different data types over here, right? So to get in a little more insight about this data frame, so we do df.info. And here we see that it's giving us a little more insight about this data set, right? So it says there are 200 entries, okay, and that there are in total 0 to 5, so 6 columns, out of which the last one is, of course, our target variable, what we want to predict in the end. And the first 5 columns are all features about the patient, attributes about the patient. And here there's something called this non-null count. So typically when you deal with different data sets, you would find that they sometimes don't have all the values filled. So for example, one patient record may have everything except the sodium to potassium level entry field. So that field may be empty. So to just put this across clearly. So over here, now for some records, maybe this field there is no value at all, like the low field. Over here, there may not be any value. So it will be missing like that. Sometimes in data sets which you'll come across in real world applications, there may be many missing values. So we cannot feed such a data set directly into the algorithm because it will perform quite poorly if we do that. So we need to substitute these missing values with some value according to some statistical measures. Like, there are many ways of filling up missing values. That's an important step in, when you want to build such models in data science. So that filling up these missing values is what we commonly refer to as data imputation. So there are many ways to fill in these missing values. You can typically people use, they would perhaps take the mean of this column and fill in, or the median, and many other ways are there. So that's what this column is telling us. So non-null count, it's telling us how many values are present in that column. So just for the purposes of today's session, to just quickly go show you through the entire pipeline, we have given you a data set in which there are no missing values. So all values are there. That's why you see that there are 200 rows. And so each column has 200 non-null. Non-null means not empty. Okay, so 200 values each. So in this particular case, we don't have to do data imputation. And it also tells us what is the data type of each column. So if you see, the age is an integer and the sodium to potassium level is a floating point, right, like the decimal. But the rest of all are all what we call as categorical. So there are so BP has now 3 categories here. So high, low, and normal, right? So that's why it says the data type is object type. So just to summarize what we have learned from this analysis, right? So that there are 5 features and 1 target value column. and that two of these features are of numerical type. So this is like integer, and this one is a floating point. But the rest other three are of categorical out of the 5 patient attributes, right? So let's now look at what are the different categories in each of those columns. So if you see, age has 57 unique values. That's because each person has some age, right? See, one person is 23, 22. So there's not really like a category kind in age. But if you take the sex column, it has 2 unique values, is what we are getting here. So we get the female label and the male label. And for BP, we have 3. So we have high, low, normal. For cholesterol also, we have 2. We have high and normal. And for the sodium to potassium, again, we have, the different floating point numbers for different patients. So that's not really like a category kind which we have here. And the drug column, as we saw before, has 5 types. So there's A, B, C, and X, Y. So ultimately, we are going to feed this into a mathematical model, which will nicely get in a black box form as a decision tree classifier. So it's important for us to translate these kind of categories to numbers. So if female and male, we'll just map 0 and 1 to it. Replace it by 0 and 1. I'll let you know what we are doing here. That's the pre-processing step. So just before that, let's separate the data set into the features and the target variable. So what we are doing is, from the age to sodium to potassium, we are putting it under features, those column names under features, and this target as separate, this drug as separate. So that's what we are doing here. So now let's get to the pre-processing, which I mentioned. So what we want to do is, instead of having string labels like this, like high and normal, we want to encode it, substitute it with some number like 0, 1, and this can be like 0, 1, 2. So that's what we mean by label encoding. So we just assign a numerical label to these categories. So first, as a first step, let's do that for the sex column. So what we'll do is, for female, we are going to replace that entry by 0. And for male, we are going to replace it by 1. So now if you look at this data set, earlier we had this female, male, male, female, etc. So now you can see that it's substituted by 0, 1, 1, 0 and 1. So I hope everyone's following till now. If there are any questions, please let us know. Okay, so let's now do the same for the next column, that is the blood pressure BP column. So here we have 3 categories like we saw earlier, right? It said there are 3 unique values: low, normal, and high. So for now, for low, we are going to substitute it with 0. For normal, we are going to put it as 1, and for high, we'll put it as 2. So let's run this. And yeah, we can take a look at how the data set looks like now. We can see that the BP column has been replaced. I mean, the entries have been replaced by 0, 1, and 2. 0 will refer to low, 1 will refer to normal, and 2 will refer to high. All right, so we'll do the same for the cholesterol column also. Yeah, here it happens so that all the first 5 entries had the same cholesterol label. So let's just look at some more rows. So I'm going to display the first 12 rows. Yeah, so you can see that some entries have now 2 associated with them. So now let's look at our information report again. We can see that the first, they were initially all object types. So these have also become integer types. The sodium to potassium level, we have retained it as the floating point. So this completes our data processing steps. So now we'll be moving on to using the decision tree algorithm. So interestingly, it's kind of how we also make decisions. Okay, so for example, if I give you like three, so this decision tree is showing us how we mentally sort three numbers. So if I give you three numbers, like say 10, 5, and say 7, then in our head, if we want to sort, what we do is we check if 10 is greater than 5. So yes, it is. Then we check if 10 is greater than 7. So yes, it is greater. So we put that, and we also in the end, and we check if 5 is greater than 7. No. So 5 comes first, 7 comes next, and then 10 comes in the end. So this is how actually in our heads we make the decision of sorting. So this is just a simple illustration here to show you. So yeah, splitting the data set. So yeah. So when we're trying to train a machine learning a model or this, this decision tree classifier, right? What we do is, so here we have 200 patient records with the associated, the target value, also the drug column, which drug was recommended for that patient. So when we are trying to train this classifier, we won't feed in all the 200 entries. In real, when you're trying to build models for real life applications, you would use like thousands and thousands of rows. Here, just for simplicity to enable you to run it on your local machine itself, you're given you only 200. But in real life settings, you would use in the order of thousands of records. So we won't feed in all the entire data set with the, with the target value to the classifier. What we'll do is we'll split the data set into two set, which is one will be the train set and the other one will be the test set. So we'll give in only the train set to the classifier to learn how to predict. Along with the train set will have both the 5, here 5, right? So both the attributes and the target value. So we'll give that to the decision tree classifier. And for that, what are we going to do with the test set? So after the decision tree classifier has trained on that train set, for testing it to see how good it is performing, we'll give only the first, only the input attributes. So in this case, only the first 5 columns. So only that we'll give it to the model. We won't give the correct answers, correct predictions. Okay. So then we are going to see what predictions it's giving for those columns. And then we'll compare it with the correct answers here. So that's what in the morning we saw precision recall and all, right? So we saw true positive, true negative. So like, or false positive. Our sample is actually belongs to the negative class, but it is falsely being put in the as a positive class and so on. So we'll see how good our model is predicting, and that's how we calculate all those metrics. Okay, like accuracy, precision, recall, and all that. So that's what we are going to do here as well. We are going to split our data set into train and test. And for that also we have useful functions, which is a train test split here. So a prior step is to put in these first 5, these input attributes into this array called X, which will be our input, and the target value column as Y. So that's what we're doing here. And we have this useful function to split our, let me close this. Yeah, so to split our, this to the train and test set. So here it says test size is 0.2, which means out of the total number of records in X and Y, we are going to put only 20% in the test set, and the remaining 80% will go to the train set. So in this case, there are 200 records, right? So 20% of 200. So about 40 records will go for the test set, and the remaining 160 will go to the train set. So that's what we're doing here. Okay, so that completes the train test split. So let me just pause a moment here to make sure everyone is on the same page. Okay, so
Excuse me, ma'am.
yeah,
I have a
I couldn't hear you. I think your audio got disconnected. Hello. I think we lost his audio. Okay. Let me continue. Maybe once he's back, we can take the question. So here we have, as part of the scikit-learn library, we have this implementation of decision tree classifier. So here we are getting an instance of that classifier. So we are called, this is a variable name. You can name it whatever you want. We have named it here as .tree. So first we get this instance of this classifier, and we have, like yesterday also we saw for the neural network, we had this dot fit function to train the model. So similarly for this decision tree classifier also, to train, it just, yeah, it's synonymous to what we call here as fit. Okay, so to train the classifier with the data, we are going to use the dot fit function. So we are passing in both the first five attributes and also the target value. So that's something to note here. Like I said before, when the training phase, we are going to pass in everything. As in for the first 160 records, we are going to pass in all the columns, including the target value column. So that's what we are going to do here. So it's done. So the training is done. So now let's just, now we are going to use this dot predict function to see what it is, what predictions it is giving for each record. So to just see how good it is performing on our training set itself, what the model has already seen before, right? Seen in the previous step. So we are going to just use this dot predict, and here you notice that we are not giving the last target value column, right? Because we want the model to tell us what they are. So we are using this dot predict function and passing in only the, you can see it's of shape 160, 5, right? So 160 rows and 5 columns. And we are going to get what are the predictions it is given, and then see how accurate it is. So to get the accuracy, we are using this function called accuracy score, in which we'll given the actual predictions, this last column, and whatever it has predicted before, we compare those two and see what is the accuracy. So you can see that here the accuracy is actually 1. So that means it has predicted correctly for all of our training set records. So now the real challenge is to see whether it's doing well on the test set, because the model has not seen the test data yet, right? So let's say use the same dot predict function, and this time instead of passing the training data, we pass the test data. So here, if you see, it's going to be 40 rows, right? Because we split it into like 80-20. 80% of the records for train and 20% for test. So 40 rows and only 5 columns, because we are not again giving the target value here. So we get all the predictions in this test array, and then we are going to compare it with the actual correct value of drug. So that's in the Y test. The Y test has all the correct answers, okay, and the pred test has all the predictions made by the decision tree classifier. And to give us more insights, as like what is the precision recall and all that, we are going to use this classification report function. This is also an inbuilt function. It's there in the scikit-learn library, and also the plot confusion matrix. I'll explain that. So let's just run this cell. Yeah. So here we can see that the accuracy is actually pretty good. We get 95% accuracy. And this is the precision recall and F1 score for each of this prediction, target value types. And this is a confusion matrix, which may be a little more interpretable. So here you can see that this is the true label axis and this is the predicted label. So let's take the last row as an example. So we had 40 records per test, right? So out of that, the 15 records had the drug Y as the actual correct value in the data given the data set. And the model also correctly predicted all of them to be drug Y. So that's what this last row tells us. And if you see here, totally there were 11 records which were there in the test set, which had the label as drug X. But the decision tree classifier, out of these 11, it correctly identified 10 of them. And for the other remaining one, it mistakenly put it in the drug Y class, drug Y label. That's what this means. So the true label for that record was actually drug X for this one, but it had put as drug Y. That is the prediction. So this way you can interpret this confusion matrix. It gives us a very quick glance of where the model is doing more good and where it's actually performing quite poor. So now, as I said before, the decision tree is very useful because it's a very explainable and very interpretable algorithm. It's very easy to understand why it's making such predictions. So this is a piece of code we have written for you to quickly visualize. So let's just run that cell. And over here, we see that this is actually the decision tree which the model has learned. Okay, so the first attribute on which it splits is the sodium to potassium attribute, and it is checking whether that sodium to potassium level is less than or equal to this particular number here, 14 point something. So now, what it does is for every new record, first it tests on this, okay? And if that record satisfies this condition, then it goes to this side of the branch, the true side. Otherwise, it's going to put that directly into this drug Y class. And next, if say that record actually satisfied this condition, so it goes here. Then it checks for BP level, whether it's less than or equal to 0.5. So here 0.5 because you remember we encoded these BP values into 0, 1, 2. So that's why we see this number kind of 0.5 over here. So if it is less than or equal to 0.5, so essentially if the BP encoded value is 0, it is going to go to the left side of the tree. Otherwise, it's going to go to the right side of the tree. So similarly, it repeats this until it reaches the end in which there are no further branches. So if you see at whichever boxes, so we call these boxes as nodes. Okay, so whichever boxes or nodes which don't have any further branching below them, we call them as leaf nodes. Okay, so we have 1, 2, 3, 4, 5, and 6 leaf nodes. So whenever we keep testing at each of this box, and when we land up on a box in which there is no further division, we can say that we have classified that sample. So you can see that if you end up here, the record will be given this drug A label. Similarly, if you end up here, the record will be given drug C label. So that completes our decision tree implementation on the drug prediction data set. We'll take a minute and then we'll see how to use this. What is this k nearest neighbors algorithm? It's a very simple algorithm, and we'll see how to use that on the same data set. So I'll just pause a minute and then we can quickly do the k nearest neighbors as well. Meanwhile, please feel free to post any questions in the chat. We'll be monitoring that. So by the way, this piece of code will also save this decision tree visualization into a .png file as an image file. So you can always use that later for your reference. Okay, so I guess we can proceed to the k nearest neighbors algorithm. So this is also a a classification algorithm, supervised learning algorithm. So here the concept is very simple. So take this example here, in which for each data point we have two attributes, so x1 and x2, and the target here is the class orange or class blue. Okay, so take some unknown point like this. No, this point over here, this green thing. It's some unknown point. Okay, we don't know yet whether it's going to be in class blue or class orange. So what this k nearest neighbor algorithm is going to do, it is going to look for k of the nearest data points. So k is basically, you can put in any number there. So if I say 2, then it is going to see who are the two, which points are the which 2 points are the nearest to this unknown point. So here say k is equal to 3. For this unknown green point, there are these 3 are the nearest ones, right? The other points are quite far away. So now it has identified that these 3 data points are the closest to this unknown data point. Now it's going to see, out of these 3, majority are belonging to which class? Okay, are they in the blue class or are they in the orange class? So here in this example, out of these 3 nearest neighbors, that's why we call them as neighbors. Okay, so out of these 3 nearest neighbors, 2 are actually belonging to the blue class and only 1 is belonging to the orange class. So the k nearest neighbors algorithm will group this unknown point with the blue class in this scenario. So you can, according to your application, and you'll be experimenting with different k values to see what fits your data the best. So that's in essence what this algorithm does. And by closest, so what do we mean by close or far away, right? So for that, we use this distance measures metrics. You would have heard of Euclidean distance, right? We, for calculating the shortest distance between 2 points, there is, we know this formula, right? So x1, if you have 2 points, x1 y1 x2 y2, then we do x1 minus x2 whole square plus y1 minus y2 whole square, the whole root. So you have this, it's a pretty common distance measure we usually use. There are other distance measure as well, Manhattan distance and etc. So basically we use a distance measure to see the nearest points to a given unknown data point. Unknown data point, by unknown I mean the class to which the data point belongs is unknown. And by looking at the majority class of its neighbors, we are going to put that data point into that class. So this is what the k nearest neighbor algorithm is. So this, yeah. So let's now use this k neighbors classifier implementation from, again, scikit-learn library. And again, we are doing the same thing. So train and test set, we'll split it and run this algorithm. So for this case here, we have chosen the number of neighbors to be 1. But I encourage you to play around with this, like set it to like 3, 4, 5, and see how the accuracy is going to get affected. Okay. So again, here also we have similar methods. So .fit for training, in which we pass the attributes and also the target variable. And then we do a predict to see what predictions it is giving, and then see how accurate it is, what is the precision, recall, etc. These are all the same functions as we have used before for decision tree, plot confusion matrix, classification report, etc. So let's just run that too. Or did I not run this? Sorry. Okay, so here we see that the accuracy has fallen quite bad. It's 72. If you recall, in the decision tree, we got 95%. So why is that? That's because we have not done this thing called scaling. So what is the scaling, right? So before I get to that, let me use this very useful function dot describe. So which is going to give us like the mean, median for each column. So as you can see here, the age column has a mean of about 44 and the max of about 74. However, if you take some other column, like say like the cholesterol column, you have the mean to be 0.97 and the max to be 2. So like I said before, we use distance measures in k nearest neighbors algorithm, right, to find which other points are near. So because the range of this age column is very much more than the what is there for the other columns, right? Even a small difference in age between two data points is going to heavily dictate the distance. So 2 points may be actually very close together, but because the age column has greater magnitudes, even a small difference in age is going to blow up that distance. So if you can see that the age column is kind of dominating here to in what will be the actual distance. We don't want that to happen. We want all the attributes to be kind of treated fairly in while calculating the distance. So what we are going to do is transform this data, apply some math on this data such that each column is falling under the same range. So not like, one column is in the order of like tens and the other column is in between like 0 to 2. So instead of that, we want to bring everything to a common range. So for that, to do that, we have, that's what is called scaling. Okay, bring all these attributes to around the same scale, same range, you will. So we have different techniques. We have quite elaborated over here. So please take a read at this, after this session. But today we'll be using this min-max scaler. So there are different other scalars. So like the standard scalar and so on. We have read, so I'll not get into too detail about what they are. But today we are doing this min-max scalar in which we are going to subtract each data entry by the minimum in that whole column. So let me open this again. So if you see for the age column, right, we have the minimum as 15. So what we are going to do is for the whole age column, for all the records, we are going to subtract that number by 15, which is the minimum for it, and divide it by the range. So max minus min. Okay, so 74 minus 15. And similarly, we are going to do that for each column individually. So what will be the result of this? Each column will have values between 0 to 1 and not this kind of disparity in the range. Okay. So for that, to do that also, we have direct implementations. So we have this min-max scalar with using which we are going to do the scaling for both the train and the test data. Yeah. Now let's again do the k nearest neighbor classifier, train it, and then see what is the result. So last time without the scaling, we had gotten about 72% accuracy, right? So let's see with the scaling whether the results have improved or whether they've gone bad. So we are using the dot fit function for training. We are using the dot predict function to get the predictions for this set of inputs. And time to see our classification report and accuracy. So you can see that accuracy has gone up. It's close to about 90% now, right? 87.5. And here you can again see the precision, recall, and all those value. And this is the same confusion matrix. So over here, we saw that actually the decision tree, it was able to classify all records of the drug Y correctly, right? Now in this case, here out of 15, it is able to correctly assign drug Y to 12 of them, and 3 of them it has mistakenly put in the drug X label. So similarly for the other rows as well. You can see for drug C, it out of the 5 records, 5 drug C records in the test set, it has correctly identified all 5 of them. So this is how you interpret this confusion matrix. And so we encourage you that here we used k is equal to 1, which is we are only seeing the nearest one neighbor and giving the class label according to it. But we encourage you to play around with this number and see whether how your accuracy is changing. So just to visualize how this data, we saw this data in the form of like a table, right? Like this. So let's see, just plot it for better visualization. So we are plotting only two columns here, the age and the sodium to potassium level. Okay, so you can see that, you can kind of see like above 15, these all are belonging to the same drug category. So here you can change, you can feed in any two of these columns, these 5 columns, any two, and you can see. So that's why the k nearest neighbor algorithm is working well. So if I give some point over here, I hope you can see my mouse cursor. So if I give you some point over here, you can see without any help of algorithm sense or something, you kind of know that it's going to be in the drug Y class, right? So that's what the k nearest neighbor algorithm kind of leverages. So if 2 points are quite similar, as in they're like close to each other, it gives that label for that record. So I guess that brings me to the end of the session. So if there are no questions, we can proceed to the next. So we'll just wait for a bit. And Santosh sir?
Yeah, tell me.
Yes, sir, I think I'm done. So perhaps if there are no questions, then we can continue with the rest of the session.
Yeah, correct.
Yeah.
Yeah, we shall wait for 2 more minutes so that people can ask you doubts.
Okay.
If not, we will hand over session to Danny and team.
Sure, sure.
I guess with no more delay, we can hand over session to Akash, Danny, Anmol, right?
Mukesh.
Yeah. Mukesh. Yeah, sorry, Mukesh.
Yes, yes, sir. Mukesh
Just a minute, Akash. I'm sorry. Harini? Okay, okay.
Oh,
You
sorry, I
continue.
didn't notice this question. Oh,
Yeah.
okay. F1. Okay. So the F1 score basically is kind of like a balance between precision and recall. So I don't want to get into it's a formula involving precision and recall. So without getting into the formula, what you can understand from the F1 score is, so basically recall is telling us, so say suppose there are like, out of 100 records, there are say 50 records of drug A and 50 records of drug B. Okay, so recall is going to tell us, so recall of drug A, if I am considering, it is going to tell us whether this model has correctly identified all of the drug A records. Okay, for drug A's recall, that's what it means. So what I mean by precision will be that, so if the model has told like 60 records out of 100 is drug A, then how many are actually drug A? How precise is it with its labeling. So that is, precision, right? But you can't judge a classifier's performance with just one of these. Okay, so because if you take, for this 100 records of 50 class A and 50 class B, if the model is saying all of the 100 as class A, then the recall for class A will be 1, which is actually and that's not good, right? Because the model has not learned anything then if it's just classifying everything as one class. So F1 score gives us this kind of balance between this precision and recall. So it's a useful measure to kind of get an overview of how the classifier is doing. I hope that clears the question.
Thanks, Arni, and Mukesh, over to you.
Sorry, Danny?
Yes, Mukesh, I'll present now.
Danny, it seems there is some sound issue at your end.
Okay. Now?
Even now,
Your background fan noise.
it might be your laptop's fan.
Is it coming also, Santosh?
Yeah.
Yeah, it is my laptop fan.
Okay.
Okay. So you can see my screen now. Hello?
Yeah, you have started sharing.
Okay. You can see my slides, right?
Yeah, now it is okay.
Okay. Uh,
Danny, try to keep any book below to your laptop, like some textbook or something. Like
1 minute, 1 minute.
it might reduce.
Mm-hmm. Yes. Santosh, I'll be back in 1 minute.
Yeah.
Hello?
Yeah.
Santosh, is it audible now?
It's audible. No other
Yeah.
sound. Yeah. But you
Okay.
can continue.
Okay. Yeah, thank you, Santosh. So today we'll see about TF-IDF, that is term frequency and inverse document frequency. What is TF-IDF? Is statistical measure that evaluates how relevant a word is to a document in a collection of documents. So it will give how important a word is to that document. So it is invented for document search and information retrieval. And this is a formula for TF-IDF. We will explore what are these, what is this formula means in coming slides. So the applications of TF-IDF are, first one is information retrieval and keyword extraction and text summarization. So in information retrieval, we will obtain information that are relevant to an query from a collection of documents. So we will we'll have some examples on these two, this information retrieval and keyword extraction. So TF-IDF made of two terms. First one is term frequency, and second one is inverse document frequency. So the definition of this term frequency is number of times a word W appears in a document divided by total number of words in a document. This TF equal to N means number of times a word appears in a document, and divided by total number of words in a document. So what is the significance of this term frequency? So like if a word occurs more number of times, that is it, if it is a frequent word, so that term frequency of that word will be high. Okay, and second one is inverse document frequency. So it is defined as the log of number of documents. See, we can see here, n is the number of documents divided by number of documents that contain the word W. This DF is number of documents that contain word W. So what is the significance of inverse document frequency is, like if in term frequency, term frequency of a word indicates whether like if a word is occurring more number of times, the term frequency will be high, and if frequency of the word is less, this inverse document frequency will be high. Okay, so see, if you want to, like I can see here, if you want to take out take out the keywords from a paragraph or text, we'll be having like if some words are repeatedly present in the paragraphs, then term frequency will be high, but they may not be the important words. So in order to catch the important words, we will combine this term frequency and inverse document frequency. So and this is term frequency formula, and this is inverse document frequency formula, and if we combine those two, no, we will get what are the important words that are present in the document. So this TF will give frequent words, this IDF will give non-frequent words. So if we combine these two, we will get like what are the most important, that what are the relevant words we can get from this TF-IDF. I will see examples also. So where this TF-IDF is applied, we can apply this TF-IDF in information retrieval. See, we can query in Google or any other search engine you like. So in a database, like see here, this is the database. So it contains some large number of documents. So if we query some text, Google will give some list of texts that are related to this query. So it may take exact words, like it will match the exact words from query and this list, and then it may give out the result like that. So this is so we will see an example now. So this is taken from this website. You can see, and they gave a nice explanation of this TF-IDF. So this is the example. See here, we have database containing description of cats. Okay, so user is querying furry cats. Okay, this is the query of the user. So we have to retrieve some documents that are related to this query. Okay, so in database we are having a description of cats, right? So we know that term frequency, what it will give is it will give more frequent words, right? So term frequency of cat will be higher, no, because it is description of cats. And term frequency of kitten will be higher, and term frequency of furry will be lower, because these two are frequent words, cat and kitten, but this is not that much frequent. And so if we see here furry cats, if we do like word to word matching from these documents, I, like without using any TF-IDF or anything, we can match to first one, like because cat is there in these two. But the underlining meaning should be furry cats and a furry kitten. Like so, in order to get that one, in order to get this thing, we will use TF-IDF. So
Danny Prakash,
yeah,
I'm sorry to stop you in between.
okay.
Like there were like some questions. One question: what is the difference between information retrieval and information extraction?
Okay, I'll answer that
Yeah.
question.
So information retrieval, you want to say just you are just taking out the information from the database, right? And
Yes.
extradition means that you are actually retrieving information in some structured format.
Yeah, that is right.
Yeah.
So, okay, I think I explain. So, the next topic we have information extraction. So, as you said, information extraction means given some unstructured text or semi-structured text, you are trying to identify key pieces of information from the text. So, what is being talked, what are the people who are being talked about in the text? What are the organizations that are being talked about in the text? What are the dates that are being talked about in the text? That is information extraction. Converting unstructured text to a structured format is information extraction, and I will cover that as the next topic. Information retrieval, as he said, is more related to something like a Google search. So you have a database of documents, and you are having a query, and you want to retrieve the related documents. That is where information retrieval comes in. And I think I'll highlight the differences as we talk about information extraction. I think we can highlight the differences further.
Okay. Generally, if we take this word matching, no, we can have this query mapped to this first document, but we like given as a result. So if we do the TF-IDF of cat here, it should be lower, because cat that is not that much important here. Here the important word is furry, like that is the most discriminative word. So here kitten also is like frequent word, but furry is not a frequent word, because since this furry word here has more discriminative power, this TF-IDF will be higher for that. And another application of TF-IDF is text summarization or keyword extraction. Like if you have watched this Mona film, the most frequent words from the Wikipedia page of Mona film are this film, Mona, the million, Disney. These are the features that we can extract from this Wikipedia page. Okay, these are the most frequent words. But but if we take another film also, like any other film, this film a word will be there, this million can be there, Disney can be there, but we want keywords that are local to Mona. Okay, so if we take TF-IDF of this film, of this Wikipedia page, we can get some good words like this is one character name in that film, like this fishhook is some like instrument in that film, like that. So like in keyword extraction, we have to take the important keywords that will have more importance, like more discriminative power. Like in most frequent words we can have all these things, but if we do classification and all, no, these things will not have that much discriminative power. These are like stop words, like that. So if you want to really classify things, we can use TF-IDF. So before that, Mukesh told us to use count vectorizer. Like if a keyword is present, we will give 1, or if keyword is not present, we will give 0, like that. In place of these things, we can give TF-IDF vector also. So going to the notebook, so we have these formulas, right? TF equal to number of times a word appears and total number of words in a document. We will convert this formula into Python code and we will see some examples. See here, are you able to see this one?
Yeah, Danny.
Okay. So here we will import some libraries, like pandas is for data manipulation, RE for regular expressions, and math is for some, we have to use this log, right? We have to use this log, no? That's why we are importing math library. So here we have two things, like two documents. So many books, so little time. And second document is a room without books is like body without soul. So in order to get TF-IDF of these words, what we have to do is we have to follow some steps. Okay, step 1 is text pre-processing. Like first, these may be in like unstructured way. In order to take them into like a structured way, we can do text pre-processing. Like most of them NLP tasks will contain text pre-processing. So step 1, we'll do text pre-processing. First we will lowercase all these things, so it will be like this, lowercase all the characters. And if see here, you can have this, you have this full stop, comma and all. No, we can remove all these things using our regular expression library. We'll substitute if if the character is not in this set with this empty character. So the resultant string will be like this. And second step is we have to build corpus. How to, we know that, right? Corpus is like a set of words, unique words from these two documents. So in order to get those set of words, first we will split the document, first document and second document, and we will get the unique words. A set of BOWA will give the unique words in document A, and set of BOWB will give the unique words in document B. We'll take union of these two, and we'll build a corpus like this. So these are the unique words. Like if you see these, like body, books, is, room, many, so, without, time, so, little. These are the unique words from these two documents. Next, count. We have to count the occurrences of each word in the documents. So this is like a feature building up a feature. Like here, these are the unique words, right? Like body, books. So, like if a word is present here, uh, you can see here. Little is present. Like is not present, no, in this document. So like is not there. We kept it as 0. And body is also not present, we kept it as 0. And books are present, so we kept it as 1. It's like count vectorizer. uh, we can use count vectorizers in place of these things also. So after doing all this, we will compute term frequency for each word. So we have this formula, no, number of time a word appears and divided by total number of words in a document. So we use a function called compute tf, and we will use this formula n by like number of times a word appears and divided by total number of words in document. And we'll see, we can see here, like this is the tf of each word. Like like because it's not there, no, in this one, so it got 0 tf. And because body is also not there, it has 0 tf. And books is present one time in this document a, so it got a 0.166. And you can see, so here, so present 2 times, no, in this document. So many books, so little times, so it got 0.33. Earlier we have said that like term frequency will be higher for the frequent words, no. So is a frequent word here, so it got 0.33. And every other things got 0.16 and zeros like that. So if it, and this is the term frequency for second document. Since here in this second document without is occurring twice, right? That's why here the term frequency for without is higher, 0.18. And even a is occurring 3 times, so we can see that a is also having some good, like relative to those, its value is higher. So we have computed this term frequency for each word. So in order to compute this TF-IDF, now we computed this one. Now we will compute inverse document frequency. So to compute inverse document frequency, we should know number of documents, total number of documents. Like this is n here, like length of documents, total number of documents divided by number of documents that contain word W. Here this value will take number of documents that contain word W. So if we pass this document A and document B to this compute IDF, it will give these results. So you can see, like 1 minute here, like wait one. Yeah, here you can see books are like more frequent ones, right? In this document also books are present. In this document we also books are present. We already know that IDF will give more weightage to rare words, like not frequently occurring words. So here books are present in those 2 documents, no, that's why it gives 0. So we computed these things also, IDF for each word. So in order to compute TF IDF, we will mix these two, like we will multiply these 2 words. like two terms. This is for ITF and this is for IDF for each word. So it will give uh, it will give like this, like TF IDF for like in this document is 0 and TF IDF for many is 0.115 like that. Okay, this is what we manual, like we can do manual, like every function we have to write and uh, everything we have to do from scratch. But Python is not like that, no? So what we can do is we have this TF IDF vectorizer from sklearn. So what it will do is it will automate all the tasks what we have did here. Okay, so first we will import the TF IDF vectorizer here, and we will import pandas and we will import arrays, and these are the documents we had. So we will initialize an object and we will use this method called fit transform on these documents. So here we took these unique words. It will automatically take here. It will automatically take these as unique words. That is like here we manually take it. May be correct or it may not be correct. But here uh, it will have some good optimization techniques. Like here you can see A is also there. We took A is also as a feature here, but here A is not there because it's not that much discrete. Like it's not that important. So it's like a stop word. So if we take these are if we give this TF IDF tokens, no, it will give all the words that are like, it will give all the feature names that what we did here. Okay, so now we will use this TF IDF WM and we will convert to array, so that will give this like a same thing here. What we got, the same thing will be reflected here. Like body word will be having 0 TF IDF in document 1 and 0.324 in document 2. See, we had like here it is 0.00 for body in document 1, but here we can see same thing, and here you can see 0.06 in document 2 for body, but here it is 0.32 for document 2. So this is more if we follow this TF IDF vectorizer, no, this is more optimized version. Like you should not use this like writing from scratch and all. If you want some good accuracy and all, we should use TF IDF vectorizer. So these notes will be sent to you. So if you have any doubts, you can. I'll stop sharing now. If you have any doubts, I'll answer them.
Excuse me, sir.
Yeah, 1 minute.
Sir, in the step 5, you mentioned some inverse documentation, something, sir. What's the use of that inverse? Why we need to take that inverse?
Yeah.
Inverse
this one,
term.
right? Yeah,
Yes,
this one, right?
term. Yes, yes.
Yeah. See, I'll explain with an example. See, TF means term frequency, no?
Yes,
This
yes.
TF. So what
Yes.
it will do, it will give like frequent terms in these documents. Like it will give more weightage to the frequent terms. Like so is there, no? It is giving more weightage to so because it is present, like it is occurring 2 times. So but this so word will not be having that much discriminative power. may or may not be having. Like if it is like a stop word, no, like if it is a or is, it can be present in any documents. Like that doesn't mean that is the main feature, right? So because for that we are using IDF, inverse document frequency. So it will give like more weightage to rare words, like which has more discriminative power.
Okay, okay. But some words we will be using in common, right?
Yeah, those are stop words. We can remove those things also. See here, film is there, no? This is using only TF, okay? Term frequency or frequent words. Here, film is there, no? It can be in any document, like it can be monofilm or any other film. Okay, but if we use this TF IDF, no, this character name movie is there, no? This is local to this film only, this monofilm only. Because we are using IDF, that's why we are getting this this as keyword.
Excuse me, sir.
Yeah, yes.
Yeah, sir. IDF means if the term is available in other documents.
Yes.
Then we will give more weightage, or then we will give less weightage, according to IDF.
Yeah, if it is present in more documents, we will give less weightage. It
Then
will only
less weightage.
Yeah, less weightage. See, you can see here like here.
Danny, this is Shivaselvan.
Yeah.
Just to add on to Danny Prakash's explanation, see the forcing limitation of the term document frequency notation, right? Because you can have some documents or a collection of documents whereas some set of words, right, really start dominating over the others, right? So in that scenario, right, that is what he is meaning the infrequent one. Some rare words, right, may never get or may never be part of my learning mechanism at all, right? So what the notation they came up with is you have this term document frequency, meaning each term is present in how many times in each document, right? Yes, it's the inverse of it. So it's almost like doing a one by like time and frequency domain you do, right? Frequency is one by time, or other way around you look at it, right? So this is just to bring down the that is what he said, stop words, some words, and all. If you keep retaining them, right, then naturally words like the, this, and all, right, we will keep occurring possibly even 500 times, right, in a large text corpus, right? So at least to mitigate their effects, we do a IDF. But it is up to you for the application, right? If you feel, right, you will have a very you will not have scenarios where such rare words, right, will have to be parsed, right? Then you can live with TF notation or TDF notation. Okay. But in a way, you can view your IDF as a normalized version.
Yeah, thank you, sir. You are very right, absolutely right, sir. Because I'm already TF and IDF.
Yeah, correct. I just wanted to add on, right? Good, great. Go ahead. Danny, sorry to interrupt.
Sir?
Yeah, so there I would use the IDF because the same thing I am performing means by removing the stop words. So if we remove the stop words, then we can't see the words that is occurring more times, that is having more value. So that's why there I am not using IDF, I am using only TF. I'm making use of TF only.
Correct, you are right. And just to give you some additional inputs, the stop word and stem word removal, right? In fact, 10 years before, that was actually steps or pre-processing steps when we handled text documents, right? That is what I used to even have it as part of the process. But during a recent interaction with some of the industry persons, right, and their input is also valid in a way, they say, right, in some cases, presence of these stop words and stem words, right, it's actually helping in identifying the context better, right? For example, in a Google search, right, the presence of I hope people are understanding what I mean, right? So I think slowly the industry is going to be set up that the stopping and stemming, right, they want to undo that, because in some cases these words actually help me in resolving the context of the search better. right? When there is a the, this, that, I hope people understand it, because for a grammatically error-free sentence, some of these stop words will come as part of the query as well, right? So there is also a complementing to emerging nowadays that don't leave off the stop words in some words, because that may help you in returning more precise results to the user, right? So in that context, then the IDF may help.
Absolutely right, sir. So
Yeah,
truly, sir.
thank you. Because I want the people to know that the stop word and stem word culture is slowly kicking out. Okay. But for a long time, stemming and stopping, right, has been there in literature for a long time. But off late, I got to know from industry personalities. Like he said, no, don't remove the stop words in some words because it helps solving the context more better.
Okay, sir.
Great, yeah. Good. Danny, I'm sorry to
Okay.
interrupt. You can continue.
Okay. Hello, this is Mukesh. I think we'll go to the next topic. So I'll just be sharing my presentation link once again, because I think I have some links for my some demos, online demos, which are already public demos. So you can try it out along with me. Okay. So it is available in the docs, like as the third last chat. You can just open it along with me. Okay. So the next topic that we are going to be talking about is information extraction, right? And as someone correctly pointed out, let's say we have some unstructured text, right? Let's say this is a paragraph that's pulled from some website. We have some unstructured text, right? So the structures, the document is not having any such structure as such. It is unstructured, right? How do we go ahead and automatically extract structured information from unstructured text or documents is what information extraction is all about, right? And this process involves multiple subtasks, which we will be looking at along the way, right? So how do we extract useful information from this piece of text is what information extraction is all about. And the first subtask along that direction is something we call as named entity recognition. So named entities in text means any mentions of real world entity. It could be a reference to people, it could be reference to organizations such as IIITDM, or it could be reference to places like Chennai, Bombay, or it could also be other things that we want to capture, right? So let me go ahead and just let me open this demo so that you get to know what named entity recognition is. So let me just pull out a random article, let's say from Wikipedia, and let me just put it down. Let me just ask the model to parse it, right? So this is a public demo which comes as which is the same named entity recognition that's available in Spacey models. So the Spacey library that we used in the morning. So you can see that the model has identified that Satya Nadella is a person, right? Indian American is a proper noun, or it's a nationality. Microsoft is an organization. Steam Bomber is a person. 2014 is a date, and it has again identified that Microsoft is an organization. So being able to identify people, or places, dates, or other things, maybe if you would select some more, you might be able to extract some more entities, right? Okay, so here there are only these, right? So this process is called as named entity recognition, right? And this is so that was named entity recognition for English language. Let's say your question would be, where do I use named entity recognition, right? So one such example where we could use named entity recognition is, let's say I want to parse a resume, right? So let me say the entities are the name of people, the designations that they hold. See, name of people, it has been parsed and it has been retrieved as an entity, right? The designation that they hold and the organization, so the designation and the company they worked at have been also identified. So this blue color is the designation, the black color is the organization. So you want to extract any structured information from unstructured text. It could be resumes, it could be news articles, it could be any particular domain articles. So you have to train entity recognition models that is specific to that particular domain. And entity recognition models for general English language is available publicly in a lot of places, and even for specific domains it is available, right? So that was the first step towards extracting information. But here there is still a problem, right? See, there is a thing like subject matter expert. There is an organization name, and there is another title and another organization name. How do I know with which title which organization name goes, right? How do I know the relations between the entities? That is where the next task comes in, right? So I think I have a notebook for the exact same demo I showed, which uses Spacey. So in interest of time, I think I'll just it is all available in the drive link that I have shared, and you should be able to try it on your own. It's just 3-4 slides. So I think in the interest of time, I think I'll just since I have shown you a demo, it's the exact same thing that you will get, but you will get in a format that can be used for other downstream tasks, right? You can use it. You can perform other tasks upon these entities, right? So the next task, as I said, is associating the relation between the entities, and that is where the next task comes in, which we call as relation extraction, right? So okay, so you can see here that I have identified. I have 3 sentences. And I have identified the relations in these sentences. I have identified the entities in these sentences. And I have defined a set of predefined relationships, like located in. So between an organization and a place, there could be a located in relation. Between an organization and a date, there could be an established in relationship. Between an organization and a person, there could be a owns relationship. So these are some predefined classes that I have defined. And I try to identify, is there a relationship between the 2 entities? And if so, what is the kind of relationship that exists between these entities? That is where the next task called relation extraction fits in, right? So I have IIITDM is an organization, Chennai is a place, and they have a relation called located in between them. Let's say the director's name is there and the organization names is there. So we have a work set relationship between both of them. So we are slowly bringing in structure into the unstructured text, right? So we are able to extract useful pieces of information and provide structure to the text, right? So let's look at another. Okay. So this is general English language, right? And as I showed, you can also like a totally different area you could use relation extraction and entity recognition is giving structure to biomedical documents, right? Let's say that this is the sentence you get. You give it to a trained entity recognition and relation extraction model. It identifies that this is a brand, this is a drug, and this is a drug, this is a brand, and this is a group of drugs. And it identifies the kind of relation. Although there is no type associated here, the relation extraction module will actually identify the type of relation, whether it's a mechanism relation between two entities, or is it an effect relation, or is it an advice relation, or is it an int relation, or there exists no relation between these 2 entities, right? They're unrelated. So this is totally another totally another domain how we can use information extraction, right? Okay, so let's so I'll just show you a small thing. Okay, let's just go for a regular expression online. Let's just take a regular expression online. Let's just so that I can show you something. Okay. So let's say I am building it is just to motivate the next task, right? So let's say that I am building a question answering session, right? Let's say that Akash has a pet dog. Akash likes the dog, right? He went to the market. Let's just name the dog something, right? Called Jimmy. Went to the market to buy food, right? Now let's say I'm building a question answering session a system or something, right? And I scan through a lot of documents and I come up with a very robust regular expression that would able to tell me answers for particular questions. So let's say the question here is who went to the market, right? Let me say someone went to the market. A to Z, let me say plus, and then let me say something like went to the market. Okay. So the thing becomes like, right. So I use a regular expression to find out where this piece of information is occurring, right? He went to the market, and my question answering session would throw out. If a question answering session would system would throw out he went to the market, but that's a very stupid answer to throw, right? Who is that he? That is where the next task called co-reference resolution comes in, right? So let me take this sentence and let me go ahead and let me put it into my co-reference resolution demo. So I have pasted some links for co-reference resolution demos, and let's just open any of the online demos, which are pre-trained models which have been trained for general English language. So you can see that Akash and he, so let me just change it to he here as well. So it identifies that these three entities refer to the same, these three references are to the same entity, right? Akash, he, and he. And a pet dog called Jimmy and the dog all refer to the same thing, right? Now, if I were to return Akash instead of he, it would be a much better answer for the question answering session, right? So this is where the next module or the next task that we are introducing happens to be useful. In tasks such as question answering and others, it is very important to know what are the entities that refer to this, what are the entities that are referring to the same thing, right? So that is where co-reference resolution comes in, right? Okay, so this is an example of co-reference resolution as you have seen in the demo. So the sentence here is that Barack Obama nominated Hillary Rodham Clinton as his Secretary of State on Monday. He chose her because she had foreign affairs experience as a former First Lady. Here you can see that Barack Obama, his and he all refer to the same entity. Hillary Clinton, the Secretary of State, her, she, and First Lady all refer to the same entity, right? So able to identify which of the entities are referring to the same thing is what is co-reference resolution all about, right? Okay, and you could actually try very complex, more longer documents as well on these co-reference resolution demos that I have shared. So you can just, they may not work 100%, but they work to a really good extent. So you should be able to see that these blue are referring to one entity, these green are referring to one entity, this red is referring to another same entity, right? And there are also nested entities inside one another, right? I think you could take some time after the session to just try out some of these demos. Maybe they would help you understand what these tasks are. Okay, so I think I'll move on to the next topic, which is called as document summarization, right? So, okay. So, okay, what is document summarization? So, document summarization is essentially, as we are all aware, it is generating, given a huge document such as a Wikipedia article, it is generating a set of summary sentences that capture the essence of the document, right? And there are two popular summarization techniques. So the first one is extractive summarization, right? You pick out important phrases and sentences from the document to make up the summary. It's like just like you are reading a document, and as you go along, you highlight the important sentences, right? So that's called as extractive summarization. There is the sentences as is from the document are extracted and they are stitched together to make a summary. And abstractive summarization is more involved and requires a lot more resources and a lot more. It is more difficult than extractive summarization. It is just like you reading an article and writing the essence of the article in your own words, right? So I just wanted to show you this thing. So you could just click the link. which is a example of extractive summarization. Just give a minute. So as this loads. Okay, so this is a paper on abstractive and extractive summarization using a deep learning model. And the surprising thing is in the abstract of this paper, right? So let's just go ahead and read the abstract, right? So what it says is that we present a method to produce abstractive summaries of long documents that exceed several thousand words via a neural network abstractive summarization technique. We perform a simple extractive step before generating a summary, which can then be used to condition the transformer model on relevant information before so it's an abstract of the thing. But the last line says that the abstract above was not written by the author. It was generated by one of the models presented in this paper. So what the abstractive summarization model has done is that it has parsed the paper and it has itself written the summary. It has summarized the content in the paper in the form of a summary. So this is one of like an interesting work in abstractive summarization. Although it is hard and the accuracy of abstractive summarization or the performance of abstractive summarization models could not be necessarily very good, but it is a very interesting area of field where models are itself reading through documents and are able to produce summaries and abstracts, right? So this paper presents a model that can do abstractive summarization of research papers, and the abstract of that paper was written using the model that they trained, right? So they're presenting in this paper, right? So that's an interesting thing in the area of abstractive summarization. Okay, so let's look at an extractive summarization algorithm, right? Which is called as text-rank, right? So as I said, I'm given a document which is a news article which has around 24 sentences in all, right? So I have to identify which of these sentences are really important to the document, and those sentences will be included in the extractive summary to capture the essence of the document, right? So okay, so let me say I include these sentences because I think if I include all these sentences, I would be able to capture the essence of the document, right? So how does extractive summarization, a text-rank algorithm for extractive summarization work, right? So what I do is that I represent each of the sentences in my document as a vertex, right? So each document in the sentence is a vertex, and I define relationships between them that have a certain weight, and the weight between the relationship is how similar these two sentences are, or is this sentence talking about something in this sentence and is this sentence talking about something in this sentence, right? Let's say the sentence 2 is talking about something in a lot of sentences, then if I'm able to produce sentence 2, I would be able to cover a lot of the topics that are covered in these sentences, right? It's a kind of it's kind of identifying the important sentences in a document, very similar to identifying the important web pages in a net, right? So who's the most important web page in a in the network of web pages, right? Or the link or web of websites, which is the most important sites? The problem is very similar to that. Who is the most important sentence that I should be including in my summary, right? So the second step is what we do is called as we use the popular Google's PageRank algorithm on this, right? So let's say that I just use my pointer. Let's say the sentence 8 happens to be an important sentence, and the sentence 6 also happens to be important sentence, and these two important sentences are talking about some sentence, then this sentence becomes important, right? Right, it's kind of the recursive PageRank definition that we are right. So someone important is talking about this web page, someone else important is talking about this web page. This guy is important. Now this guy is talking about him. and he's an important sentence, this guy becomes important. It's a kind of recursive definition, right? And you get a page rank scores, right, which tells us how important each sentence is for the document, and we sort the sentences and get the highest ranked sentences as this set of summary sentence for the document, right? So there is a notebook which essentially I have and it should be available in the drive link that I have shared. If not, I think Akash shared it a few moments ago, but I'll just share it if in case you need it. Okay, so this is the drive link. So you can just see that it uses the same summarization algorithm. Okay, so what I have done is that I have just taken Wikipedia article on automatic summarization, which is a very huge document, and I have just copy pasted that into a string, right? It's just a document on automatic summarization on Wikipedia. I have copy pasted on that onto a string, right? Let's just run it. So I'm just defining the Wikipedia article, which is the same article I have pasted in as a text, and I'm just defining a summary, defining a function to format the summary list of some summary sentences that I'm getting, right? So I'm going to be using a library called Gensave, and I'm going to be using the summarize function, which is there in the summarization module, which makes use of text rank algorithm, right? So what I get is I get a list of summary sentences, summarize of text, and please give me a summary which has not more than 300 words, and please give it to me as a list. I get a list of summary sentences, right? And as I said, it's an extractive summarization algorithm, which means the sentence as is should be available in the document, right? See, so the sentence as is available in the document, and because I have just added new lines, the sentence is not matching. So each of the sentences is assumed to be important by the algorithm, right? So since I have included new line characters, I think it is just having some problem. I think if I make it, yeah. So this sentence is as is available in the document. So that is why it is called abstractive summarization. It hasn't paraphrased the sentences to write the summary. It has extracted important sentences and presented them as the summary of the document, right? Okay, so I think you could have a look at the sentences generated. And as you can see, it's an unsupervised algorithm. Like we do not have a training set where we have a set of documents and the summary sentences for it, and we train a model, and then we are using that model to get the summary sentences. It's an unsupervised approach where every time you have a document, you create a graph of sentences, and then what you do is that you run a PageRank algorithm on the graph of sentences, and you get the important sentences. So it's an unsupervised algorithm and not a supervised algorithm, right? Okay. So I think you could be looking into these notebooks. I already shared the drive, and everything should be available in that. And we will share it once again. Okay, so another, let's say we talked about question answering in the morning, and I just wanted to share another important sub aspect or another important task, which is at the intersection of NLP and computer vision, right? So that task is called as visual question answering. So given an image, you ask a question, and the question answering system returns the answer, right? So this is the image, and asking what are the animals in the scene, and the system should be able to say that there is a giraffe in this image. And such kind of systems require a lot of training data, where you have lots of images and lots of questions and answers associated with the images, and you use them to train your network. So there is also a demo available with this. So so that you just to show the power of NLP and deep learning for a lot of tasks. So you can just click any of the images. So these are all public demos which are there. So you can ask, you can ask questions, what is there in the image? And it should be able to retrieve one word or two word answers for these, right? It says a stop sign is the image. Is the light in the image red? Question mark. Or let's just say it's in green. It says no. And you could you could just ask such questions, right? Right. So this is called as question answering, and mostly these are achieved using deep learning models. Right. Okay. And another task would be machine translation. All of us are aware of Google Translate, right? So right. So we have a source language and we want to convert to a target language. We have lots and lots of training data of the sentence in the source language and the target language. So we can train systems that can translate from the source language to the target language, right? So such systems are like Google Translate are also NLP systems. Okay, I think I'm done we are done with the basic tasks in NLP, and I'll just summarize the various tasks that we have seen it. So at the syntax level, we have parts of speech tagging, which is associating the parts of speech tag with each token. Then we have parsing, which is creating dependency tree, or parsing and identifying what is the parsing the sentence, just like we parse programming languages. Then we looked at named entity recognition, relation extraction, named entity recognition, relation extraction, and summarization, co-reference resolution. And we have also other types of systems such as dialogue systems that not only need to be able to answer questions about an image, but also need to be able to have a context across questions or across the throughout the conversation. It needs to be able to maintain the context of what is being spoken, right? Such systems are the ones that have the ability to capture the discourse information in a conversation, right? Yeah, I think that's it for basic NLP tasks. If you have any questions, then we can take them.
Mukesh.
Yeah.
Right? Mukesh, Akash, and right, I hope if Arani is there, I think she would have left. Arani is there. All four of you, right? Excellent effort, yes, right? So you are satisfying yourself, students. I think that's not the intent, right? In fact, the way he took up research papers, right? The way what Mukesh did it, right? I think that's why I think the first go-to for me when it comes to Python, right? It is these trusted lot, right? Akash, Mukesh, right? All four, Harini, right? None is above the other or none is below the other, whichever way you put it, right? See, I think that's what I also put it in the chat. See, I am around your, I think some of them are senior to me, some of them are around my age, right? We know our attention span. I think you ask us to deliver 5 hours, right? We are ready to do, but sit for 2 hours, it's really difficult, right? It's nothing offensive. I can understand the pain, all that stuff, right? So I am not expecting that you will master all NLP Python skill set in one session. That's not happening, and if that happens, something seriously wrong is happening. Okay, right? So I think all the students or the industry expert speakers, right? I keep calling them as students. They're my past students. Their email IDs, right? We will share it to you. Hopefully, you will have, right? Or by the shortly you will get it, so that you can be in touch with them. Let's assume somebody is working on text processing only, right? So those guys, right? Maybe you can get in touch with Mukesh or Danny, right? And somebody is working on neural networks, right? Deep learning, Ishan, Harini, right? I'm very sure the students, right? They will give you the pointers, right? because I think practical skill set, right? You possibly cannot get it in a 2 hour, and that to post sambar or lunch. Okay, right? But we can't avoid it here, right? We have to run it as a sequential event, right? But I'm very really thankful for my. Yeah, we will hold nothing. At least my students also believe in the open source culture. Everything will be shared here, right? Hopefully, things are going into that YouTube channel, video and all, PPTs and all. Don't worry. We will set up a website, right, where we will consolidate the PPTs so that you can click the link and take. If possible, post the consolidated. Okay, right. You are asking the most difficult ML question. Okay, right. So kindly share. Santosh, you can share the YouTube channel to them. Yeah, right? I think it could have been done earlier. No issues. You can send it to them. Okay. Attendance, be rest assured, right? Because I think my TAs as well, right? And my courses also running parallelly, right? So we will consolidate it. Don't worry. Normally, we don't reveal to the students, right? I'm not meeting you, the typical classroom, right? Because the numerator gets adjusted according to the denominator. Okay. I hope you people are understanding what the numerator and denominator means, right? We'll take care. Don't bother, but ensure that you are in the room. Okay. In network issues, you are logging in and logging off. That the app takes care. Okay. First 2 days we will take it. Google Drive link to share. Please keep on adding. Fine. They will do. Human mother. No, today we are not giving because I think there are a lot of confusion yesterday. That is why we have gone in for an automatic attendance tracking app along with Gmeet, right? So even if you exit due to internet issues, it will automatically track your next entry, multiple entries, everything is tracked. That is why it will take time for us to consolidate. As long as you have been in the room at some point in the session, you don't have to be worried. Okay. Kindly share, Mukesh, sir, everything will be done. Don't worry, but give them some time because all of them, mainly my Santosh and Mercy, right? They are actually maybe I think Santosh, you can give the email IDs. Okay, I think that will go to all broadcasts, right? Okay, put it in the drive here. That's it.
Okay, sir.
I'm not asking immediately. I understand your time constraint, right? So good. I hope people are enjoying the workshop, right? And my personal take is the Gmeet session is much more automatic, less monotonous, right? Because I think we are never exceeding size 100, right? So I think we can continue with this syntax. Okay. Okay, you people can take a break, 15-minute break if you want, right? For 4:45 to 4:50, you join back. Santosh, you can stop recording for a while.